So we start with this first presentation. It's a presentation to talk about the hydrology modeling. It's let's say a thing that is exclusive for SewerGEMS and for other product called SilverStorm. We will be seeing how does the hydrology work in these products. So let's talk about the difference between hydrology and hydraulics. So different people use different definitions for hydrology and hydraulics, and the dividing line between the two. For example, the hydrology, we can say that will be converting all the rainfall information to inflow, and the hydraulics will be used to get the results about flow, velocity, hydraulic grade line, and etc. In combined sewers, almost all runoff reaches combined sewer, where you can have runoff flows going directly to your sewers if we are talking about combined networks. This water can be originated by precipitation from inflow and other situations. In sanitary sewers, stormwater is supposed to be kept out but enters through system defects like infiltrations through cracks, infiltrations at manholes, or even inflows at manholes. And how does the wet weather flow get into sanitary sewers? So it depends of each situation. So our main preoccupation is to understand how our system works. So infiltration can be from leaks, bad joints, bad taps, leaky manholes, and inflows can be from storm drains, roof leaders, catch basins. Different components are necessary for different systems. Talk about the loading approaches. We have for stormwater networks the runoff method, and for combined sewers we have the combination from runoff plus the dry weather flow. And in sanitary sewers we have another parcel called RDII. It's the rainfall derived infiltration and inflow. It's a defect flow. In SewerGEMS we have the load builder tool to help with this loading approach. With load builder we can use the GIS input to load all the sanitary sewers from water meters, and then we can also use load builder to load dry water flow from areas with density and census numbers. Now applying the wet weather flow, we have three general ways in SewerGEMS that can be combined. On conduits, we have an option to load infiltration. As we can see in this picture at the left side, we have infiltrations to be entered by pipe length. The pipe length method is the most common, where you put infiltration rate by a loading unit, like cubic feet per second, every each yard or every each feet. At the manholes, we have an inflow option. The inflow option, it's an option separated from the sanitary load option. It's the same approach, but this data is loaded in a different alternative. And the third way is using catchments. It's a polygon that will perform hydrograph calculations. Comparing each solver that we have in SewerGEMS, we have here a table that we can see that not all methods are available for each solver. So the implicit solver contains all the infiltration methods, but the explicit solver just have the infiltration flow. The implicit and explicit solver are can be found in SewerGEMS and SilverStorm. The GVF convex is also available in SewerGEMS and SewerCAD. The GVF convex is for a graduated varied flow with convex routing. And the GVF rational, it's just for StormCAD and SilverStorm, and it's focused in rational method for stormwater calculations, and it doesn't have options for pipe infiltration calculation. This course deals primarily with the precipitation, infiltration, and direct runoff components of the hydrology cycle. In some situations, the groundwater table may rise right enough to affect stormwater conveyance systems. The complex interaction between groundwater and surface runoff will be not covered in this course. Regarding the hydraulic cycle for precipitation and evaporation, it can be held by the SWMM method available in SewerGEMS. For the wet weather loading, the calculating runoff involves a combination of accounting for losses and converting the available runoff into sewer flows. So after modeling catchments, we need to put the precipitation information and, if needed, a loss calculation. Normally, the loss calculation is a rate that will be used to calculate the amount of water that will be carried by the network. Talking about the precipitation, there are lots of ways to enter the precipitation data. We don't do the snow melt yet in our softwares. So accessing the storm data menu, we have some options to import from rainfall curves. We can use the engineering libraries to save and store your most used precipitation information. You can create from equations, IDF equations, or you can use your own curve. Just entering a storm event doesn't tell the model which one you use for a run. So after defining your precipitation, the next step is to define the storm event that you need to use. You can set a global storm event or even a local storm event. Now, overview about catchments. The hydrology is performed just on this kind of elements. Each catchment has a single outflow point where it enters the collection system. So it's a polygon. The software has some layout tools for delineation. You can use Model Builder to import CAD file or a GIS or shape file to import and automatically have your polygons on the system. Each catchment has an outflow element that needs to be a node like a manhole or a catch basin. In this element, you need to identify the loss and the hydrograph methods and specify the time of concentration. And if needed, you can define a local rainfall for your catchment, or if not, you'll be using the global rainfall event. Regarding the loss and hydrograph methods, for loss we have these methods listed in this presentation. The most used is the Soil Conservation Service curve number, the SCS option, or the Green-Ampt curve. For the hydrograph methods, we also have the SCS method, the SWMM method, or other methods like HISAX, time area, modified rational, and other unit hydrograph methods, such as the RTK and the generic option. For loss methods, the SCS method is more applicable for large lands, but it's used for many places. It's based on a curve number. Water infiltrates into the soil, and the effective precipitation is available for runoff. The Horton's equation uses an exponential decay of concentration rate versus time. The Green-Ampt is the most theoretically correct method for infiltration. It requires considerable information on soil's properties, like capillary suction, saturated moisture content, initial moisture content, accumulated infiltration, and etc. And for the hydrograph methods, for combined stormwater, we have the CSS method, EPS swim, modified rational method, and USEX. And for sanitary, we have the generic unit hydrograph and the RTK method. For time of concentration, we have these 17 different methods available. Normally, you need to use what your local government indicates. For the SCS unit hydrograph and other unit hydrograph methods, depending of the size of the catchment, we have a defined number like 15 minutes or 5 minutes. So the time of concentration can be also a user-defined number instead of using equations. Here's the EPA SWMS nonlinear reservoir model for runoff. User must supply the catchment width, the depression storage depth, it's the DP number, and its slope and roughness, as well the percentage of impervious area. The unit hydrograph is the most used. It's a curve that represents the response of the catchment to a specified amount, like a unit number that can be 1 centimeter, 1 meter, or 1 inch of excess rainfall occurring over some duration. The generic unit hydrograph option, it's a basic equation as shown in this slide that can be also an option to define the hydrograph method. And this is what you get for a runoff with the SCS unit hydrograph. QP and TP are derived from the time of concentration and catchment area. The RTK hydrograph method, it's a special case of generated triangular hydrographs from sewer flow monitoring and precipitation data. It fits triangular hydrograph using 3 parameters, RTK, Three triangular hydrographs, each with its own RTK, are commonly used due to need to model different processes: rapid inflow, intermediate infiltration inflow, or long-term infiltration. R is fraction of rainfall entering sanitary sewer. T is time to peak in hours, and K is ratio of recession time to T. RTK is a special case of generating triangular hydrographs based on sewer flow monitoring and precipitation data. User must specify three parameters: RTK for each of three components: rapid, moderate, and slow RDII. This shows how the three components hydrographs of the RTK methods are combined to make up an hydrograph. The RTK component, the coefficients: large R means persistent, large T means slow response, large catchment, large K means long recession. Determining coefficients for hydrographs, especially for sanitary system, is one of the most tedious and difficult steps in modeling. It usually requires flow and precipitation monitoring. These numbers must be calibrated, and it is very important to get the most accurate model to represent your real system. Next, we have a table to compare the runoff method available for each solver. So for the implicit and explicit, we can see which one we have available. So for implicit, we have all runoff methods except of the rational method. The explicit is an option that has all the options but not the rational and the time area options. Now talking about the rainfall derivative, infiltration, inflow. People have tried to use a lot of different methods to model sanitary sewer inflow. It's an option that can be used by a constant unit rate, a correlation with stream flow, percent of rainfall, unit hydrographs, or the RTK method. You need to separate the dry and wet weather flow from your monitoring data because you need to model them individually. This is an overview of taking monitoring data, converting it into modeling coefficients, and then using it to drive the model. So first, you need to define the data that you have to get from the field. So having all the information for the dry water condition, will be performing a statistic calculation called regression to get all the coefficients for the dry weather period, and then starting in the next option, in the next situation, to model the wet weather event, having the precipitation event, developing the RDII flow, and then assigning it to the nodes to finally to run the engine and getting your model with both wet and dry weather flows. In flow monitoring, you need to look at the incremental flow from each monitoring station. Sometimes overflows upstream of the monitoring point gives misleading hydrographs. Once you have a flow at a meter, you still need to decide how to spread it out to the nodes. Usually you just spread it out, and load builder can do a nice job to do this for the dry weather flow. This is a case to apply the GIS information having polygons, and for each one we have an area for the dry weather flow calculation. If you have storm or combined sewers, methods like the SWMM, the soil conservation service, and etc. work well. Any method can work. If you have sanitary infiltration in flow, you are uncentered as to how wet weather water gets into sewer. So you must use a calibration-based method like RTK or generic hydrograph.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.